We are ready to look at the third method for determining the delta H of a reaction. We did calorimetry, we did Hess's law, and now we're going to utilize something called enthalpy of formation. So this is a way of going to tables, and there's tables full of these values, and manipulate those values to come up with a delta H for a reaction. Those tables had utilized calorimetry, they had utilized Hess's law to come up with very specific reaction values, okay? So what we need to do is we need to define what's called a standard enthalpy of formation. And here is the definition, okay? First of all, the symbol, it has a little F, that stands for formation. So whenever you see a delta H and then a subscript that says something like an F here in this case, or it could say combustion or whatever, it is describing the reaction. The reaction this is a delta H for is called a formation reaction. And the other little thing we see with the symbol is a circle there at the top, and that little thing means it's in standard state conditions. Okay? So this is going to be the heat change that results when a very specific reaction takes place, and that is we are going to form 1 mole of a compound. And what are we going to make it from? We're going to make it from its elements in their most stable form, okay, under standard state conditions. That circle, again, it stands for standard state conditions, and the standard state condition is 1 atmosphere if it's a gas. Now if it's aqueous, it's going to be 1 molar, but we really won't run into that much right now, but that's a standard state condition. The pressure of those gases would be at 1 atmosphere. All right, so like I said, it's a very specific reaction it's giving you a delta H value for. So often when we go to the tables, it will tell me that the temperature is 25 degrees Celsius. That is not a requirement for standard state conditions. It's not like STP, standard temperature and pressure, where you have to have standard for both of them. But those tables most commonly are reported at 25, and these values change somewhat if the temperature changes. So that's something to be aware of. And like I told you already, standard state conditions of 1 atmosphere or the 1 molar, that's what that little circle, that little degree looking thing stands for. All right, in your book there is a table that gives values for it. There's an appendix that has them in the back of the book, way more of them than are in the table. When you do your homework, very often there's a little link for click here to see standard values, and it brings up a table for you on the computer with all sorts of values of delta H of formations. We're not ready to use it yet. What we're ready to do is really think about that reaction and that it's describing. When I look up the delta H of formation of magnesium carbonate, that's all it'll say. It'll say magnesium carbonate, and then it'll have a value for the delta H of formation. And let's say when we look it up, it's a negative 1112.9 kilojoules per mole. What we need to understand is what this means. I don't want you just using numbers to solve these problems. I want you to understand the underlying meaning of enthalpy of formation. So what we're going to do is we are going to form 1 mole of the magnesium carbonate. Okay, so we would put that magnesium carbonate on the right-hand side, and then the elements that make it up on the left-hand side. See what we see there? We've got magnesium, so we write magnesium. Magnesium is a solid under standard state conditions, so we put an S after it. Carbon, the most stable form of carbon is graphite, so we put Gr after it. Oxygen, it's diatomic. Elemental oxygen is the most stable form. It's a gas, so we write that there. And then we balance it, but we have to balance it keeping a 1 mole on the product side there. We don't want to balance it with the lowest whole numbers. We want to balance it keeping the 1 mole on the right-hand side because of the definition. It is, by definition, making 1 mole of the compound from its elements. Okay, so any substance in there, when they give you a delta H of formation, it's for a very specific reaction, which we see it being described there. Okay, so I want you to take that information and tell me, if I went to a table and I looked up the heat of formation of CH4 gas, which one of those reactions is the heat of formation reaction? Stop the video, choose one, and then resume. Whoops, back up. I didn't have a little green star pop up there. Well, let's see. We should have come up with answer. Now, I didn't put the GR. carbon graphite is a solid, and I just put the S. So you might have said, well, none of them are right because I don't see a GR, but it is a solid, so that's what's written here. Making 1 mole of the product. Well, I can eliminate A because it is not making a mole of the product. It is making the product as a reactant, so we cross off A. I cross off D because it's not making 1 mole of CH4, it's making 2 moles of CH4, so it can't be D. This leaves me with B and C. B, the elemental form of hydrogen is not H, it's H2, so that leaves me with the answer being C. So if you chose C, you were correct. Okay, let's try another one for you to think about. All right, let's say we wanted to know the delta H of formation of O2. I want you to stop the video before you do. Think about what I'm saying. I want you to go back and look at the definition of heat of formation, making 1 mole of the substance from its elements in its most stable form. And once you think about that, can you come up with an answer for this one? Did you think about it and come up with an answer? Well, the answer is C, and we need to think about why that would be. By definition, heat of formation is making the thing it gives you the heat of formation from, which we're trying to do it for O2, and you're making it from the element in its most stable form. And what's the most stable form of oxygen? O2 gas. So when I write that, did anything happen? Nothing happened. If nothing happened, then the delta H of this reaction has to be 0. And if the delta H of this reaction is 0, and that reaction is a formation reaction, then that means the delta H of formation of oxygen, elemental oxygen, O2, is 0. Now I expect you to know that for any other elemental forms. In its most stable form, the delta H of formation will be 0. Now let's see how we would utilize this. Here we go. So the delta H of formation, what we'll do is we'll sum up the delta H of formation of all the products, that's the final stuff, minus the delta H of formation of all the reactants, that's the initial stuff, okay? So that symbol there that we see, okay, this symbol, that's the summation symbol, right? We're going to add them all up. We see the N in that equation, we see the M in that equation. Those stand for the coefficients that we see in the balanced equation. So with that equation, we'll work on this. I'm going to start you going, and then you're going to finish it off. We look at the equation, and we want to know the delta H of this reaction. And if we're using tables of standard heats of formation, then we're going to end up with a standard delta H for this reaction. We look at the product side, and we see that we have 4 moles of the CO2. And then we're going to need to have the delta H of formation of CO2. Okay, that's the first product. We are adding these up. So then we're going to add to that the delta H of formation of the oxygen, but we have 2 moles of that oxygen times the delta H of formation, I'm sorry, it's not oxygen, it's water. The delta H of formation of the H2O, and it is a liquid in this case. While I'm thinking about it, make sure you're very careful when you go to tables, because I've pulled out the right ones for us down here, but when you go to tables, it'll have H2O liquid, it'll have H2O gas, it'll have H2O solid, and you need to choose the right one for your problem. So that is the summation of all the products. And then you are going to, it's products minus reactants, you're going to subtract from that all of the delta H of formations of the reactants. So I have 2 moles of the C2H2 times the delta H of formation of the C2H2, okay? And then we have, for the oxygen, we have 5 moles of O2 times the delta H of formation of the O2. So those are my reactants, products minus reactants. Now, at this point, I've kind of gotten you set up. I want you to stop, put the numbers in, and see which one of those answers you get. Once you've caught a value that's up there, resume and let's see how you did. All right, did you choose A? If you did, you were correct. If you got this, you know how to plug it in and you're raring to go. If you didn't, Maybe you got D. You got to be really careful with the sign. I'm pointing out things that are common mistakes. Students will a lot of times do this plus this, and they'll not notice I'm subtracting this. Or they'll take these two numbers and they'll subtract the first one and then they'll add the second one. But you had to subtract the whole thing there. Now, did I give you the delta H of formation of oxygen? I didn't. Why not? Well, because that value, I expect you to know, is a big 0 kilojoules, okay? It takes no energy to do that for the reasons we talked about up here. So that would be a common mistake, is to forget to double things, forget to put these in, forget about the sign here that this is minus. You just be meticulous of plugging your stuff in and you'll be okay. So go back and see if you can redo it and see if you can get that negative 2598.8 kilojoules for your answer. And if you have any problems with this, let me know. We'll see other variations of this in class and work on this some more when we practice in class.